So I record these office hours. So we've got shit and we've got not shit on these resonance hybrids. And so there's going to be like a big ass delta negative here and a big delta positive here, and a very small delta plus here and a very small delta minus here. And sort of this, you can subtract this little bit of delta plus from this little bit of delta minus and still humongously delta minus. Like the overall contribution of the resonance, this contributes like 99 to 1. So, and since they're directly opposite each other, it's just basically 98 of this. So, yes, when you do resonance and you break a bond, you always break it so that you make the more stable positive charge and more stable negative charge, because the other thing can happen, but it's overcompensated by the right one happening.
So I can't break that other double bond and just throw it to another carbon?
Well, you can.
Oh, okay, because that's like what my brain wants to do.
So what? So we want to throw this to this carbon?
Yeah, like can
That's
that
good.
happen?
Yeah, then that's perfect. So then we'll have this double bond like that, right?
Can that happen first instead of breaking the oxygen double bond?
Yes. So let's say we do sort of. So I'm going to put a little caveat there. So yeah, you can do that. Like if you want to do that, then this carbon here is going to be making 5 bonds.
And it's going to be
break a bond with it.
Okay.
But what you can do is you can do that. Oops. Just delete the double bond. You can do that, and then you can do that. That's fine. So then, so then one of the questions that you get is, okay, why did I break the bond this way and not the other way? Because in both cases, it's a negative on a secondary, positive on a secondary. And I think the only answer to that is you need to consider the molecule as a whole. So if I do that, and I look at this, and I know which way that carbonyl is going to break, because unlike the carbon-carbon double bond, there's no, carbons are carbons. This is definitely going to go one way versus the other. And if I did this, then I've got 2 positives next to each other, which is really bad. Whereas if I had broken it the way I broke it at first there, I'd have sort of negative, positive, which is, really good.
Okay, that makes sense. Thank you.
Does it? Okay, thank you. Yeah, Felicia. Felicia asked, can sodium hydride and LDA be used interchangeably for alkyne reactions? Yes. They're both strong bases. They can be used interchangeably. Do you have another question, Megan? You still have time.
Yeah, I don't know how to find the solvents and solutes when I have like the products and the reactants. I don't know how to find those middle ones.
So what you need to identify is what the hell is going on. So if we have an example, this is where you just need familiarity. So what you need to identify is what has happened. And so what you need to look at is, okay, I've taken a double bond, and I haven't drawn it in, because I don't need to, but I've added H and OH across that double bond. So I've added water across double bond. Okay. Cool. How do I do that? Well, I know I can use acid and water to do that, but that would give me the Markovnikov product. And so what I expect if I added acid and water to that thing on the left, I would have gotten that. And that is not what I see in my compound there.
We
So
want
I want
anti-Markovnikov.
anti-Markovnikov. So what reagent do I use for anti-Markovnikov?
No clue, dude.
So this is where you need to sit down with all the reactions we've done, and literally, I'm not fucking kidding. Draw flashcards or something, or a table, or a sheet, or like a description of the reagents and what they do. Yeah, Nicolas Borain, and that's correct. So BH. So the right answer is, well, one of the right answers.
Yeah, I don't understand why BH3 though, because that doesn't have OH in it. And that
Well,
just
you
throws
add
me
the B.
off.
You add these guys afterwards. So
Oh,
BH3 adds the boron. So I think this was one of the earlier class, first class or second class when we were trying to talk about alkenes. So BH3 adds the boron here, and then the sodium hydroxide, hydrogen peroxide displaces that with water. And again, we covered the mechanism when we went through the alkene stuff, so I'm not going to do it again now. But I think what you might need to do is go through all the lecture notes, go through all the this stuff, and draw up lists of these things. If it's an
okay.
open book
Cause
exam, you don't need to memorize it.
yeah, because like I don't understand like when I need to use like THF and those ones and stuff. They just really throw me off.
Well, so the solvents are mostly, for the most part, the solvents are interchangeable. A lot of the solvents we've been doing for almost everything are, when in doubt, using polar aprotic solvents. So you can do almost any reaction THF or dichloromethane. Almost anything will work in either of those solvents. The times when we start picking out the solvents is when we're really looking at sort of E1 SN1, E2 SN2s. Um, and then you just need to make sure your solvent's not going to react, or your solvent does react if you want it to react. So if you want to add an ethanol, if you want to add an ethyl, if you want to add an ethanol group, then use ethanol as solvent. Don't use butanol as solvent. But um, that's the only time the solvents are really, really interacting with things. Otherwise, you can basically dump in. You can use these for basically everything.
Okay. Thank you.
Yeah, yeah, useful stuff in a chat. So I'm not sure. I think Emmanuel is here next. I think that's the way the window's working, but I'm not sure.
Nadia was here before me. I'm not
Okay,
sure if she
not
has
hi
a
Nadia.
question.
Okay, that's the way this works. Okay.
Hi, I didn't have any questions. I was just here to listen to other people's
Okay,
questions.
so Emmanuel, you're up.
All right, I'll share my screen if that's okay.
Yeah. I'm gonna just stop sharing mine.
All right. Uh, my first question comes from assignment X. It's yeah, 3A. So why'd you decide to like organize the bonds like this and put the negative charge here?
I just did.
So could we have done it like could we have kept it here if we drew
Yeah,
this
you could
one?
have kept it there. It's completely right. Because notice that wouldn't have changed any of the orbitals. All the orbitals would have been exactly the same.
Okay. So when you have a lone pair on a carbon, it stays in a p orbital, right?
Yeah.
So do we have to indicate that or no? Or can we just draw the p orbital?
I didn't draw any electrons there because they kind of move. So it's hard. So because I'm drawing a linear combination, you can. It wouldn't be wrong.
Mm-hmm.
I'm just drawing it that way. It would have been. It would have been wrong to put them into like an sp. It would have been wrong to draw that as an sp3 carbon.
Okay.
Um, but I wasn't writing the electrons into the p orbitals there. I wrote the lone pairs into the fluorines. It wouldn't be incorrect to do that. It would not
All
be,
right.
but it's not going to be incorrect to do that either. What I just did there.
Okay, and then okay, that makes sense. And then I have another question from assignment 3. It's this one right here. So I get like the entire mechanism of how we have to like add.
Yeah, but I had the brom. I did that backwards. I still need to go and correct that. Yeah.
Right, but then my question is, so it would attack the iodine, right?
Yeah, absolutely.
But then when you attack the iodine, wouldn't the positive charge go here? Because that's the more
Yep.
substituted
Yep.
carbon,
So
and
you
then
I get the wrong product.
the bromine. Okay, so this is even like this even
You
like
would
this
need to
entire
use. You
question.
would actually do a radical reaction with that, with BRI, and that would invert it
Do a radical reaction with it.
because you would have you'd have the iodine radical be more stable.
Okay.
So your radical would attack. You'd have the Sorry, that's not going to work. The answer might not be answerable.
Okay.
Um,
Yeah, if these were swapped though, it would be.
I think I have to swap them. I think I have to go into the answer key and swap them.
If these were swapped, it'd be possible.
Yeah.
Okay, and then I had one more question, but like it's not loading. I'm not sure why. But what it was
Delete that question.
a question on Mobius. It was, I think it was to determine whether or not molecules were chiral. And then the molecules was symmetrical, but on one side of it, like the fluorine was wedged, and on the other side it was dashed. Everything else was the same. So, like when there's wedges and dashes, like can you still consider that? Like, can you still like draw a line of symmetry between them? You know what I mean?
Yeah, you can draw a line of symmetry right down the wedge and dash, middle of that. I can't remember what the exact example was.
It was yeah. I don't know why it's not loading. I don't know how else to show
I
it to
don't
you.
know why Mobius seems to be causing some trouble now. Is it with all the assignments or just this one?
I only tried this one, but yeah,
'Cause it
no, it's
seems to have
not.
just been in the last few days. Suddenly, Mobius has decided to do something. Which assignment is this? This is
It's assignment, like it's the first real one.
okay. Let's see. Yeah, I think that's the one. I'm wondering if like there's something like it's timed out or something. Maybe I need to reactivate it. Um, teaching. No, no. Oh, where the um. Nope, not that one. Oh, okay. I think I. Do you want to stop sharing for a second? I think
Yeah.
I found what I'm looking for, but we need to find the right one. Okay, it was this assignment. It was one of these
Oh,
questions
it was A, on the bottom right. Yeah,
with the two methyls.
yeah,
Right. So that's basically asking: is there a plane of symmetry here? And there's no obvious plane of symmetry.
yeah, exactly.
So then I think what you need to do is you need to figure out because you can have something whose mirror image is its own compound, in which case it's a meso compound.
Mm-hmm.
So all compounds with an internal plane of symmetry are meso, but not all meso compounds have an internal plane of symmetry.
Okay.
And so maybe one way to think about that is what we can do is we can rotate this molecule. So I'm going to stop sharing for a second. I'm going to just share on my tablet. Hopefully we can sort of work this one out. So but if I rotate that bond, all I'm doing is rotating around this bond. So I'm keeping this half of the molecule steady, and I'm flipping this half of the molecule. Do you see what I'm doing? I take it that's a no. Oh, you're muted.
Oh, sorry, I was muted. Yeah, I understand.
And now we have an internal plane of symmetry.
Okay, so then like when it's because that was my question. So when it's one is wedged and one is dashed, you can't like I couldn't just draw a plane of symmetry between the bond
Well,
connecting
you could
the-
try, and it's like, well, there's nothing clear there, but what you need to do is maybe you don't have the thing in the right rotation to draw the plane of symmetry.
Okay.
And so I can rotate this molecule. It's the same molecule. I haven't changed the molecule. It now clearly has a plane of symmetry.
Yeah.
It's just in the previous way I had it rotated, it wasn't.
Okay. Okay, that makes sense. All right, yeah, that's all my questions.
Cool.
Okay, thank you.
Okay, I think that means you're up next, Keith.
Okay, can I share my screen?
Yeah, stop sharing.
I just had some questions about assignment X. Okay, for question 1F, I was wondering, could you do another resonance structure after 3 where a lone pair on the oxygen comes down?
To where?
To the right, so that it makes a double bond with the nitrogen.
Yeah.
Okay. And then for
I think so. Look, just go back. Let me double check that before I just say yeah. Yes, absolutely. Nitrogen has just lost something. Yeah, I'm not actually sure why I didn't draw that one because it's a good lone pair. That's a really good resonance structure.
Okay, and then for 1H, I was wondering, in the structure that's labeled 3, so is that positive charge? I thought it was an sp, or like I'm confused about what orbital that positive charge is in.
That positive charge, is seeing in a p orbital,
Okay.
but it's bad to have it on an sp2 carbon.
Oh, I see.
It's not an sp2 orbital. It's in the positive charge is there's an empty p orbital.
Mm-hmm.
That's maybe the better way to put it. It's not sort of sitting in anything because it's like an absence, but there is an empty p orbital.
Oh, okay.
But it's worse to have a positive charge on sp2 atom than on a sp it's sp. I don't know why I wrote sp2. It's worse to have it on an sp atom than an sp2 because I'm just trying to figure out my math there. Yeah, that should read sp.
Okay.
Yeah.
And then if this was a lone pair, would then that be an sp orbital?
If that was a lone pair, it would still be in a p orbital. You'd have to remove the hydrogen that's on there.
Yeah.
In the sp. If there was a negative charge there instead of a positive, that would be 2 electrons in a p orbital.
Oh, okay.
Assuming they could do resonance. Now, if you just took that molecule, compound 3, swap the positive charge for a negative charge, then that would be in an sp2 orbital. Because it would not be able to participate in resonance.
Yeah. Okay.
I think.
Oh, for LCAOs, I was wondering, do we need to integrate like wedge and dash?
It's good to draw some three-dimensionality.
Okay. And then I was also wondering,
it's important for that middle carbon, for example. Those fluorines probably doesn't matter, but that carbon that they're attached to, it's relevant that that's tetrahedral.
Sorry, can you repeat that?
So for the fluorines, it probably
Mhm.
doesn't matter very much for the lone pairs, but for the carbon they're attached to, it's important that there is that wedges and dashes. So I
Okay.
just get in the habit of that. Yeah.
Okay. And I was wondering, like, how many pi bonds do we need to draw? Because aren't like all of these p orbitals interacting?
They are, but only for whatever reason I dropped the pi bond on the alkyne, the second pi bond on the alkyne. I should have drawn that in. I just didn't indicate it for whatever reason.
Mhm.
But there's only one pi bond that can be occupied by those top three p orbitals. Like one of them's pi, one of them's got 2 electrons.
Oh, okay.
Like the LCAO shows us that all these can interact. Like all the green orbitals can
Mhm.
interact with all the, like they're all in a network. Like those
Yeah.
are all sharing electrons.
Mhm.
And you can draw excuse me, 2 bonds between any set of them and have a lone pair in a third set. And there's 3 different ways to do that, and they're all valid. And those things are always kind of interchanging. Like they each have an electron kind of in them, and they're each sort of sharing around. And there's an extra
Oh,
in the system.
okay, so we should only group 2 of them at a time?
Yeah,
Okay.
because that's what a pi bond is.
Mhm. And then, oh, my last question. Oh, I was confused about this statement where it says a carbocation is worse than positive charge on an oxygen. I thought the other way around was true.
So again, is it an 8 electron oxygen or a 6 electron oxygen?
It's 8 electron.
Right, and the carbocation is a 6 electron.
Oh, okay.
So doing the full octet's more important.
Oh, okay.
So having a positive charge on the full octet is always better than the atom. So yeah, it like if you have a 6 electron oxygen and a 6 electron carbon, it's better to have it on a carbon for sure. But an 8 electron oxygen is formally positive, but not really positive. It still's got 8 electrons.
Okay.
Yeah.
Okay, that's all. Thank
Yeah.
you.
I think Bennett. I think you're next.
Just hanging around and listening, taking notes.
Okay, Mariam.
I'm just listening.
Okay, Mohammed. I know you got cut off last week, so I'm going to skip. I said you could jump to the front of the line because you got cut off yesterday.
Hi, sir. Good morning.
Yeah.
I just had a couple of questions with regards to the assignments. So
Yeah.
I'm just going to share my screen.
Okay.
All right. So this is the first one, and to the left you said that this is the best structure, and to the right you said that this was the second best.
Yeah.
But when assigning, the best resonance structures, you always want the negative charge on the most electronegative atom. So, and O is more electronegative. So, how come it's
So you want it on electronegativity across the row, size down the column. So S stabilizes a negative charge better than oxygen, just like I stabilizes a better negative charge better than fluorine. So I minus is more stable than Br minus. S, even though it's Br minus, is more electronegative because size matters.
okay?
So down the column, it's all about size. Across the row, it's all about electronegativity.
I see. Okay, that makes sense.
Yeah, so that's why S is more stable than S minus is more stable than O minus.
And also, when determining like a better resonance structure, where does induction come? Like in terms of priority?
It's kind of tied with hyperconjugation, depending on how extreme the differences in hyperconjugation are and how far the induction effect is.
Yeah.
So, yes, they are in competition. Like a CF3 group that is 6 atoms away from your charge isn't very important. Is it induction? Yes, absolutely. Is it important induction? No, because it's 6 atoms away.
That makes sense.
Just like, and it might matter a lot if you're comparing a secondary carbocation with a CF3 group next. Okay, like a secondary carbocation, nothing really donates by induction. So a secondary, okay, let's go with the secondary carbanion with a CF3 group next to it versus a primary carbanion. The primary carbanion is better than the secondary by induction. Sorry, by hyperconjugation, or by density of donation and all that. But the CF3 group by induction probably, well, it does overcompensate that small difference. But if
Right.
you're comparing a tertiary carbocation and a primary carbocation, then small inductive effects down the line don't matter as much as tertiary versus primary. So they're kind of, it's wishy-washy.
Yeah, and I remember you saying something like, it won't be, you know, ambiguous on the final.
No,
Like,
it won't be.
Yeah. Right. I have another question. This one right here. So you use isopropanol to go from this right product to the left product.
I think you're still sharing the same
Oh, sorry.
picture. No worries. I do this all the time, so I'm not going to show anyone else over it. Yeah.
Right. So you use isopropanol to go from the right product to the left. And it was said that if you use something, you know, more linear, that it could possibly do SN2.
Yeah.
Is that correct?
Yeah.
So in terms of like, you know, cycloalkanes, you always have to use like, you know, like the ball kind of structures, right?
Right. What we're trying to do is we're trying to suppress SN2, and we're trying to we're trying to do the Zaitsev elimination.
Yeah.
Because if we were to do a Hoffman elimination, we'd probably eliminate the other bromine.
Yeah.
Because it's going to be that secondary CH2 on that up carbon. So yeah, it's trying to balance that. I'd accept other. Well, I think I actually gave that isopropoxide. And the boxes are empty, and so. But we could have drawn something else. But I was trying to indicate with that we're doing eliminations. That really likes doing eliminations.
All right. Yeah, that makes sense. You know, I think the only practice I need is with regards to the 4 reactions. Like everything else, to me, it's like it's not as hard. Like, you know, with enough work, it's good. But like the 4 reactions
Somebody
are
asked
tough.
me to bring up some secondary examples where we start balancing things out.
Oh, that was me.
Yep. So I'm going to talk about that next class.
Right. And last question. So in this one here, the way I'm trying to find my answer for this. Okay, so in your answer you had the OH, like here. I'll just draw. So this was your answer.
Yeah.
And I feel like I was a bit like skeptical because I feel like there's like an adductive effect from here, so like you wouldn't want to have you wouldn't want to have a positive charge in this area.
I disagree with you. So you're absolutely right that there's an inductive effect, which is bad. Stabilizing that, but there's a resonance effect which is really, really good because the oxygen of the O-methyl group can donate to a lone pair to stabilize that carbocation by resonance.
So you can like do this like that and then do this.
Yeah.
Okay. Yeah. So
now that positive looks a lot better because then we will delocalize that carbocation onto an 8-electron oxygen. No, there'll be a hydrogen up at that top one, not a positive charge. You would have added the hydrogen.
Oh yeah, for sure.
And a positive would now be on the OME.
Okay, so this is like one of the rare effects where even though you have induction, it's like it's stabilized by resonance, but usually
resonance always beats induction.
Yeah.
Always. And so most atoms that can withdraw by resonance, if they're directly attached to the center, can donate withdraw by induction can donate by resonance. And donation by resonance is always stronger than withdrawal by induction.
Yeah, I think I remember seeing that resonance is like on top of both induction and hyperconjugation.
Resonance dominates.
Yeah. All right, that makes sense. That's all my questions for now.
Okay.
Thanks. Thank you for the help.
No worries. Okay, now Mariam, I think.
I'm just listening.
Okay, sorry, Felicia.
I'm just listening.
Okay, Sporty. I have no idea if I'm pronouncing that right.
I'm also just listening.
Okay, Aying.
I'm also listening.
Okay, does anyone actually have an effing question? Gabriella or Megan?
I had a quick question.
Okay, awesome.
From assignment 1.
Yep.
Okay. Can you see my screen?
Yeah.
Okay, perfect. I just had a question why there was this partial charge here.
I put a partial negative there. Okay, I didn't end up drawing the resonance structure there. But if we take a look at the second most stable resonance structure, the one I drew on the far right.
Yep.
That one? Okay,
Yeah.
so what you can imagine if you think, actually, this kind of falls into a question that Megan asked, the other Megan asked earlier, which is that the net double bond next to it, that's still there,
Yeah.
that can do that can also break one way to make a resonance structure. You can use it for resonance. And so which way are you going to want to break it?
Pardon?
Which way are you going to want to break it? Which way do you want to move? So that double bond can break. You can move the electrons into one of the carbons and leave the other one positive. So you make one C minus, one C plus. Which way do you want to break that double bond?
Oh, you want to break it further away from the negative oxygen.
So where do you want the negative charge on the left or the right?
Okay, so like if you want the negative charge on that one left.
Why? You're right.
Is it because of the positive, like the positive carbon?
Yeah, exactly. So you want a negative next to a positive because you know that carbonyl or the oxygen carbon bond is going to break so that you have O minus C plus. That's a given. You're not going to do O plus C minus. That's stupid. You're going to do O minus C plus. But so next to that C plus, you want negative.
Okay.
So that's why that double bond is polarized to be partially negative towards that carbon. That's why.
Okay, that makes more sense now.
Yeah.
I think that's honestly the only question I had. Other than that, I just came to listen.
Okay. So Gabriella, do you have any questions?
I don't have like a specific question, but would you be able to just like quickly kind of go over how you know when it's like endothermic or exothermic for like any kind of reaction? I know it's like stability, but like sometimes I just get confused.
Yeah, no, it's fine. That is a specific question. It's actually a really good question. So basically what that means is the reaction spontaneous or not? Like, does it happen? Because exothermic reactions happen, endothermic reactions don't. And so let's say we have how you draw a transition state for a cycloalkane, like an SN2 transition state, Felicia? Like what kind of transition state? Sure, okay. You know what then? Let's do a twofer. Okay. So let's say we had this reaction. Clearly an SN2. There's inversion of configuration. We got a nucleophile. We've got a leaving group. And what we should be looking at with that is going, okay, what do I think of the relative stability of my leaving groups? So coming back to you, maybe Gabriella, on this one. What do you think of I minus versus F minus? Which is more stable?
I is more stable than
Right.
F.
Perfect. So you've gone from kind of like I've drawn it over the arrow, but essentially when we're drawing something over the arrow, we're saying it's a reagent. So it's on the left side of the arrow. And on the right side of the arrow, we have F minus. So what we're saying basically is this is more stable. And I agree with you completely. Now, can we get this to go? Yeah, we can. You know, if you add like 1,000,000 equivalents of sodium iodide, you will get this to go because there's just so much sodium iodide on there, it will push the fluorine off, give it enough energy. But this tells us that this reaction would much rather go the other way. And so this reaction, if we take a look at the reaction coordinate diagram, we have the starting material, which is more stable than the product. So it's clearly an endothermic reaction. Now, what that means is, in general, I've drawn this backwards, and probably, you know, under normal circumstances, we would flip the role of the product to the starting material. So that the reaction would become exothermic if we go from this to that. So almost all the reactions, what this basically comes down to is almost all the reactions we've drawn in this course are exothermic. Almost every reaction we've drawn in this course is exothermic. Because organic chemistry tends to be exothermic because it tends to move towards stability. And when you have an endothermic reaction, you're moving against stability. And so if we want to look at what the transition state here is, using that Hammond postulate, and it doesn't matter if we're going this way or that way over the reaction coordinate, because, you know, we're used to time going one way, but reactions can go both ways. And so you can move back and forwards along this reaction coordinate. You can go left or right. And so the transition state, though, is a point in time, and it's the same whether you're going left or right. And so for a cycloalkane, the transition state for an SN2 is always the same. The carbon needs to be flat. So I'm drawing in this thing. Possibly. Sorry, I'll finish this and I'll get to the questions that are coming up in the chat. And I'm going to look more like the product than a starting material. So my iodine bond is going to be shorter than my fluorine bond. And I'm going to look more like the product. So I'm going to see more of my charge is on my F minus than on my I minus. And this makes sense because as soon as that fluorine starts getting closer and the iodine starts taking off, the iodine is going to get more and more negative and is more likely to leave. This is kind of the transition state, remember, is the tipping point. It's the point where everything is 50-50. You can go either way. You're at the exact even point. But that looks the same whether it's the fluorine coming in or the iodine coming in. You're going to have the same transition state. And so, yeah, this is like the cycloalkane thing where somebody asked the question, can I draw a cycloalkane transition state? Yeah, you just need to keep this thing flat. This whole thing is flat. And then we just have those two coming in.
So you would just look at like the stability, and then in the transition state, you would have to draw it so that the more stable one is like the shorter like dots or whatever.
Well, yeah, well, actually, we're closer to the product, right? So what I'm doing is I'm just trying to make this thing look more like the product. The product has an iodine attached.
Oh, okay.
So the iodine is closer.
Okay, makes sense. Thank you.
Because I look more like the product. Because the energy difference here is smaller than the energy difference here. Did that answer the question?
Yeah.
Sort of? Yeah, so the reason is almost everything we're doing is exothermic. So we don't see a lot of endothermic reactions because the thing is when you have an endothermic reaction, the reaction coordinate tends to indicate, well, you're going the wrong way, Like you're trying to go the wrong way down a one-way street. Go the other way. Okay. I'm getting some support for a question. I will go over envelope conformations. On the exam, will we need to draw the negative and positive dipoles and resonance structures? Yes. Probably. Yes. You might need to. It's testable. How do you draw a transition state for an E1 reaction? Everyone wants to talk about that. Okay. So for an E1 reaction, slightly tougher question maybe than it actually seems because there's two transition states sometimes. So let's say we were doing this. So I'm doing a Hoffman elimination because I have no idea why. It's just what I drew. Okay, so mechanistically, we've actually got three separate steps occurring. I've got 15 minutes, Megan, so maybe I will do that. If you want to show up tomorrow, I will start with that tomorrow if that works for you, because it's going to take a little bit longer. And if not, if it doesn't work for you, I'm going to record it, so that'll be okay too. So the first step is protonation. This is an intermediate. It is a valid Lewis structure. The second step is leaving group leaving. This is an intermediate. It is a valid Lewis group structure. The third step is deprotonation. As a product is a valid Lewis group structure. So if we look at the reaction coordinate diagram, starting material, A, B, product. Go uphill a bit to A, go uphill a lot to B, to the carbocation, and then go downhill a lot to the product. So what we have is we have three transition states. The rate determining step is one with the biggest activation energy. And so I guess when you're asking, can you draw the transition state for an elimination E1 reaction? It's like, well, there are three transition states. But I think the one we're talking about is this one here. I think that's what you're talking about, is this transition state. And so what does that look like? Well, again, this is an endothermic step. So remember what I was saying is, overall, we don't see very many endothermic reactions. Our reactions are exothermic, and this one's definitely exothermic. Product is lower than starting material. But you can have endothermic reactions that are kind of coupled together to give you the exothermic. So what we've done is we've coupled two endothermic transformations with a very exothermic transformation. And so overall, the process is exothermic, though individual steps are endothermic. But anyways, this transition state is going to look a lot more like B than it is like A. So what does that mean? Well, it means that, we're going to still have three-dimensionality on here. We're not going to have gone SP3, SP2 at this point. We're still going to be SP3. But we're looking a lot more like B. So we have a big delta plus and a smaller delta plus here. So we're looking like that water is starting to drift off, but it hasn't drifted off entirely yet. Overall positive charge. And it makes sense when you're thinking about this a little bit, because if the water was closer to the carbocation, then it would just snap onto the carbocation, and you'd be somewhere going up this slope. You'd be below the transition state. And the most likely thing to happen when you're going up the slope is to fall back down to the local minimum. And then you get some energy, you go up, and then you fall. And you go up, and then you fall. And then you go up, and then you fall. And and then maybe eventually a molecule gets enough energy that peaks, hits the transition state. It's It's got a 50-50 shot of doing either. And at that point, you put enough energy in to pull this water. You vibrated this thing apart so that this OH has really moved far enough away from this carbon that if it moves another tiny angstrom, fraction of an angstrom, it will dissociate because now we're going to be falling down the other side. And if we wanders back a tiny little bit, it's going to snap right back on. So we're at the close. It probably doesn't. It doesn't matter. The manual, there is a difference. I'm sure they're not the same. They're different, but I've got. I don't know. They're probably pretty close. Is B higher in energy because O has a full octet A? Yes, absolutely. Yeah, the carbocation is higher in energy because OA in A, O has a full octet. That's not bad. This is not a hard step to do to add a proton to something. It's very hard to make a carbocation. So I guess this is what the transition state of the E1 rate determining step looks like. But there are two other transition states in there. I don't know if that answered the question. Sweet. So besides Megan's bigger question about determining RNS, which is a bigger question, is going to take a bit more time, does anyone else have anything else?
I had a quick question.
Sure.
I don't think it should take long. It's kind of just like a confirmation of my thinking, but can I share my screen?
Yeah. I'll just stop. And then, envelopes. We'll come back and finish with envelopes.
So for 41A, I just wanted to see if I'm interpreting it correctly.
Yeah, I'm not giving you answers to the exam, right? So but I just want to make sure I can answer if you're interpreting it correctly.
Okay. So ETOH is isn't a charged species, so it's not as strong a nucleophile base. So the middle bromine, or like the furthest right bromine, as a leaving group left, and then with that positive secondary carbocation can do resonance with the alkene to give a tertiary carbocation. And in that resonance, I did an E1, assuming that was favored due to better conjugation if you form another alkene in that bond or in that molecule. So my intermediate A would still have the tertiary bromine at the far left, and then two alkenes. And then for the next step, I'm assuming it's again an addition of ETOH, where I did an SN1 reaction with the other bromine.
I like everything that you said up to the last thing you said.
Oh, shit. Okay.
So I would just think, why didn't you do, I guess the question for you to think about is, why didn't you do an SN1 in the first step? Why did you on SN1?
In the first step, I did E1 because of conjugation.
Okay.
So I can do that again in the second step.
Is there conjugation?
There can be, yeah.
Okay.
Okay. So two E1 reactions.
I'm not answering the question.
All right.
Yeah,
that's a yes.
Policy, but okay. Your thinking is solid.
Okay, thank you.
Yeah. The reason I'm actually not posting answers to that is I use that exam for other things, and I don't want the answers posted anywhere on the internet. So it's just because I use that particular exam for other things. I'm not really, yeah. But you're thinking solid there. Okay. I think Megan, yes, I think I am. Because why not? Whew. Huh. It's a good question, Felicia. Um, I think the textbook probably does have some things and like tying it all together. I hope. Um, and like what we've done in class have been harder questions than what I'm going to ask you guys to do. Man, they're really specific what you're doing with retrosynthesis in the textbook. I think, unfortunately, the answer I've got for you is no. I got my assignment questions. Now you got me thinking that what we really need is like a book of problems in organic chemistry, like at the introductory level. Because I'm actually really kind of disappointed in how few problems are in a textbook. Maybe I need to write a book of organic chemistry problems and then actually check the answers before I post them. So no, I don't. I don't think so. I don't think, but I think. I think you can turn almost any of the problems into something like that. Like any of the problems I posted, you can almost go backwards on them, sort of try and meet things in the middle. And that those network questions that I have in the assignments and in the practice exam are kind of that kind of retrosynthesis thing. Because sometimes you can't figure out what the box is going forward, but you can figure it out by going backwards. And so it's basically asking you to kind of fill in this puzzle. Yeah. I'm sorry, I wish I had a better answer for you than that. And I'm just, I think it's really, really important. And you're right. Almost everything else I can point you towards online resources or something where you can do more practice problems. But on this, I don't think that's really a thing that they're doing very much on. Okay. Okay. You don't. So I will never ask you for a retrosynthetic analysis on a question here on the exam. I want to introduce the concept so you can start thinking that, oh yeah, I can go backwards. Now, a lot of you probably could do this anyways. You'd be doing it anyways. But just for anyone who didn't catch that, it just sort of formalizing and saying, hey, yeah, there's a name for this. And somebody won a Nobel Prize for giving something obvious a name. But you don't need, you're not going to need to provide a retrosynthesis of things. You can always just go forward. But it's a useful tool to be able to kind of work both ways. Okay. I am going to stop the recording and I'm going to post this recording and we'll go from there. I will see some of you tomorrow morning at 9 a.m. and maybe anyone else in class.